Well, I think that there's increasingly a convergence actually between SpaceX and Tesla and XAI. It's going to be, I think, if you can think of it, you can have it, will be the future. Then I would say that's probably a good company to invest in. When Tesla is doing simulations for self-driving.
There is a rule in the automotive world that nobody ever wrote down, but every engineer on the planet quietly obeyed it. You could build a car that was fast, or you could build a car that was efficient. You could not, according to that rule, build a car that was both. For more than a century, that trade-off was treated less like an engineering challenge and more like a law of nature, something as fixed and unbending as gravity itself. Then, a small team inside a Tesla facility was given an assignment that sounded almost boring on paper: design a motor cheap enough to put in millions of ordinary cars. What they handed back didn't just meet the brief, it quietly broke the rule the entire industry had agreed to live by. This is the story of that motor, why Tesla needed it more than most people realize, and why some of the smartest engineers in the business think it will take their competitors the better part of a decade to catch up. To understand why this engine matters, you have to go back to a time almost nobody talks about anymore, back when Tesla was the underdog nobody expected to last. In the early years of the electric vehicle boom, Tesla was the smallest, scrappiest name on a list dominated by giants. Ford, General Motors, Toyota, Volkswagen. These were companies with 100 years of manufacturing muscle behind them, global supply chains, factories on every continent, and enough cash reserves to survive a decade of mistakes. Tesla had none of that. It had ambition, a handful of factories, and a stock price that swung wildly with every rumor. The conventional wisdom at the time was simple and, frankly, reasonable. Tesla might have a head start, but head starts in manufacturing don't last. Once the legacy automakers decided to take electric vehicles seriously, they would apply their scale, their supplier relationships, and their decades of production expertise, and the gap would close fast. For a while, that prediction looked accurate. Rival electric vehicles genuinely improved. Battery ranges climbed faster than expected. Interiors got nicer. Prices got more competitive. And analysts started writing headlines about Tesla's shrinking lead. The underdog story seemed to be wrapping up exactly the way underdog stories usually do, with the giant eventually rolling over the upstart. Then, something changed the conversation entirely, and it wasn't a flashy new model or a clever ad campaign. It was a piece of hardware buried deep inside the car, the part almost nobody outside the engineering world ever thinks about: the motor. When veteran teardown engineer Sandy Munro and his team took apart one of Tesla's newest drive units, they were not expecting to find anything revolutionary. Teardown specialists see hundreds of components a year, and most of the time, the surprises are minor. But this time was different. As Munro's team dismantled the motor piece by piece, they kept circling back to one particular detail wrapped tightly around the spinning core, a component that, on the surface, looked almost unremarkable. It wasn't unremarkable. It was the reason this motor could do things that shouldn't have been possible in a mass-market car. What made the moment notable wasn't just the performance numbers. It was the realization, shared quietly among people who spend their careers picking apart cars for a living, that Tesla hadn't simply improved on the old formula. It had stepped onto a different playing field altogether, one that most competitors weren't even positioned to reach yet. Here's the part of the story that rarely gets told alongside the engineering breakthrough. Tesla didn't unveil this motor purely out of ambition. It needed a win, and it needed one badly. The Cybertruck, once marketed as the future of American driveways, had become something closer to a cautionary tale. After years of hype, teaser events, and a launch that dominated headlines for weeks, actual sales numbers fell well short of expectations. Recalls chipped away at consumer confidence. And in a market that suddenly offered a dozen credible electric truck and SUV alternatives, Tesla's most talked about product wasn't pulling the weight everyone assumed it would. Reports even suggested that a meaningful chunk of Cybertruck registrations in certain quarters came from companies tied directly to Elon Musk himself, essentially internal purchases, propping up numbers that otherwise looked thin. For a company whose entire brand identity rests on the idea that everything it touches redefines its category, that was an uncomfortable position to be in. Musk needed something undeniable, Not a paint color, not a new dashboard animation, not a marketing stunt, something structural. Something that changed what was physically possible rather than what was merely fashionable. Around the same time, Tesla dramatically raised its spending plans, pushing capital expenditure guidance north of $25 billion, with big chunks of that flowing into artificial intelligence, robotics, and custom silicon. The company was betting big on its next wave of technology. The question was where the next headline-grabbing breakthrough would actually come from. The answer had been quietly spinning inside a lab the entire time. To appreciate why this particular motor mattered so much, you need to understand the trade-off it destroyed. In a traditional electric motor, the rotor, the spinning heart of the machine, is under brutal mechanical stress as speeds climb. Push it too fast, and centrifugal force starts trying to tear it apart from the inside. Traditional rotor designs simply cannot survive extreme rotational speeds without warping, weakening, or failing outright. That physical limit is precisely why automakers were stuck, choosing between blistering acceleration and long-range efficiency, chase performance, and a motor overheats, guzzles energy, and demands a bulky cooling system. Chase efficiency, and the car feels sluggish, lacking the instant punch drivers want. Tesla's engineers refuse to accept that ceiling. Instead of optimizing around the edges of the old design, they rebuilt the core component from scratch, wrapping the rotor in a shell of carbon fiber, a material prized in aerospace and motorsport for being remarkably strong while weighing almost nothing. That carbon sleeve acts like armor, holding the rotor together under stress that would tear a conventional design apart. The result is a motor capable of spinning past 20,000 revolutions per minute, a figure that historically belonged to specialized industrial equipment, not the family sedan idling in a school pickup line. But raw rotational speed wasn't actually the headline achievement. What mattered more was stability. The carbon wrap dampened vibration and kept the spinning rotor perfectly balanced, and that balance translated directly into sharper magnetic performance. In simple terms, more of the electricity pulled from the battery turned into forward motion, and less of it was wasted as heat, noise, and vibration. That single shift rippled through everything else about the car. Less wasted energy means more usable range from an identical battery pack. Less heat means a smaller, lighter cooling system, which frees up space and weight that can go toward batteries, cargo room, or simply a lower sticker price. Every rival automaker still has to bolt on pumps, radiators, and coolant lines just to keep a conventional motor alive under hard driving. Tesla effectively deleted a large slice of that complexity. The public got its clearest look at what this technology could do behind the wheel of the Tesla Model S Plaid, a car that uses 3 electric motors to produce over 1,000 horsepower and rockets from a standstill to 60 miles per hour in barely 2 seconds. Numbers like that used to be reserved for 7-figure hypercars, not a 5-seat family sedan capable of hauling groceries and children hundreds of miles on a single charge. Knowing the idea behind a carbon-wrapped rotor is one thing. Manufacturing millions of them without bankrupting your production line is an entirely different challenge, and this is where Tesla's real advantage lives. Picture what the process actually demands on a factory floor. Carbon fiber tape, delicate and pre-impregnated with resin, has to be wound around the spinning rotor core under exact, unwavering tension. Wind it too loose, and the rotor flexes and fails once it hits real-world speeds. Wind it too tight, and the fibers themselves crack under their own stress. The whole assembly then has to be cured under precise heat and pressure. And even a small miss in temperature or timing ruins the part completely. After all of that, every finished rotor must be balanced to a tolerance most factories never have to think about, because a wobble that would be invisible at ordinary highway speeds becomes a violent, self-destructive vibration once the motor is spinning at 20,000 RPM. A competitor can't simply photograph this component and reverse engineer it in a weekend. They have to rebuild an entire manufacturing process around it, absorbing the cost of every ruined rotor along the way, learning the same painful lessons Tesla already worked through years earlier. Some industry analysts believe that gap alone could take rivals close to a decade to close, and by the time they get there, Tesla will likely have already moved the target again. If the engineering story wasn't enough to unsettle rival automakers, the economics should be. Tesla has stated its goal of getting the entire drive unit motor, power electronics, and gearbox combined down to roughly $1,000 to produce. Some competitors reportedly spend 3 to 5 times that amount just to achieve comparable performance. That gap sounds abstract until you multiply it across production volume. A difference of even a couple $1,000s per vehicle spread across hundreds of thousands of cars a year becomes the kind of margin that can quietly fund entire new product lines, research divisions, or aggressive price cuts that rivals simply cannot match without losing money on every sale. Tesla isn't stopping at cost reduction through better engineering either. The company has been working to strip rare earth materials out of its motor magnets, reducing its dependence on a supply chain concentrated heavily in a small number of countries. That matters more than it might sound. The refining of key rare earth elements used in high-performance motor magnets is dominated by very few global suppliers, and that concentration hands enormous leverage to whoever controls it. Prices can shift overnight based on a single policy announcement. Shipments can slow during a trade dispute. Every automaker leaning heavily on those materials is, in a quiet way, building its cars on someone else's permission. If Tesla can meaningfully reduce that dependency, it isn't just trimming cost. It's stepping partially outside a pressure point that has worried the entire industry for years. A parallel effort is underway to reduce reliance on costly silicon carbide semiconductors in the motor's power electronics. Again, lowering both cost and exposure to a narrow field of suppliers. Put simply, cheaper production enables lower prices. Lower prices pull in more buyers. More buyers mean higher production volume, and higher volume builds the kind of manufacturing experience that drives costs down even further. It's a cycle that feeds itself, and every rival chasing it is chasing a target that keeps moving. While Tesla was refining this cycle, most of its rivals were losing money on the electric vehicles they already had on the road. Ford built genuinely well-reviewed electric vehicles, yet its electric division reported enormous losses. Companies like Lucid and Rivian earned praise for their engineering and design but continued burning through cash at an alarming pace. Even giants like General Motors and Volkswagen have faced software delays and mounting questions about long-term profitability in their EV divisions. The one major global rival that still looks capable of matching Tesla at scale is BYD, but its strength comes primarily from flooding lower-cost markets with affordable vehicles rather than combining performance, efficiency, and desirability the way Tesla is attempting to. Being cheap is one competitive strategy. Being cheap, fast, efficient, and aspirational all at once is a far harder trick, and right now almost nobody else is pulling it off. Here's where the story stops being purely about a motor and becomes something bigger. Tesla's real advantage isn't any single piece of hardware. It's the way the company has fused several industries into one interconnected machine, with the drive unit sitting at the center feeding everything else. Start with data. Every Tesla on the road continuously gathers real-world driving information, road conditions, driver behavior, weather, rare edge case events. Autonomous systems improve the same way a human driver improves, through repeated exposure to real situations. And Tesla has accumulated more of that raw driving experience than almost any competitor on the planet. More cars on the road generate more data. More data trains smarter software. Smarter software makes the vehicles more desirable, and more desirable vehicles sell more cars. A cheaper, more efficient, harder-to-copy motor means more Teslas on more roads, which means the entire data engine spins faster. Then there's the battery business. Tesla poured billions into producing its own battery cells, aiming to boost energy density while cutting cost and manufacturing complexity. Most competitors still rely heavily on outside battery suppliers, which means paying a markup on the single most expensive component in any electric vehicle. Owning that piece of the supply chain lets Tesla design the battery and the car around each other from the earliest stages, rather than fitting a car around whatever cells a supplier happens to offer. The supercharger network tells a similar story. For years, critics dismissed Tesla's charging stations as a nice perk rather than a genuine competitive advantage. That assumption aged poorly. Tesla's charging network became known for reliability and ease of use at a time when rival networks were frequently plagued by broken equipment and confusing payment systems. Eventually, several major competitors, including Ford and General Motors, adopted Tesla's charging standards so their own customers could access that network. It's an unusual position to be in. Rivals now depend on infrastructure built by the very company they're trying to beat, and Tesla gathers useful data on charging patterns and demand every time a competitor's vehicle plugs in. And underneath all of it sits Tesla's investment in custom computing infrastructure, built specifically to train artificial intelligence on the flood of driving footage collected from its global fleet. Rather than renting computing power from outside providers the way most rivals do, Tesla chose to build much of that infrastructure itself, betting that its long-term value depends less on the cars it sells today and more on the intelligence those cars will be capable of tomorrow. Put all of it together, and a pattern emerges that should genuinely concern anyone trying to catch up. A better motor lowers production cost. Lower cost raises performance per dollar and attracts more buyers. More buyers generate more real-world driving data. More data trains smarter software faster. Smarter software improves autonomy and overall vehicle value. Higher vehicle value funds further research into better hardware, which leads to the next version of the motor being even more capable and even cheaper to build. The cycle doesn't just repeat, it accelerates. For rival automakers, the uncomfortable truth is that they're no longer competing on a single front. They're being asked to simultaneously match Tesla's motor design, battery technology, software stack, manufacturing efficiency, charging infrastructure, and artificial intelligence capability, all built by different teams on different timelines, often relying on outside suppliers for the pieces Tesla has chosen to build in-house. Catching up on any one of those fronts individually would take serious time and investment. Catching up on all of them simultaneously is a challenge almost no company on Earth is currently positioned to pull off. The motor that stopped a veteran tear-down engineer at his workbench was never really the finish line. It was a signal, a quiet demonstration that the old rules everyone accepted as unbreakable no longer hold. Instead of a level playing field with a handful of automakers trading the lead back and forth, what appears to be forming is something closer to a single company pulling steadily further ahead, not because any one part is magical, but because so many parts are reinforcing each other at once. Whether that lead is truly unassailable or simply looks that way for now is genuinely up for debate. Manufacturing gaps have closed before. Supply chains shift. Regulations change. Talented engineers move between companies. And breakthroughs elsewhere in the industry could shift the equation again. But for the moment, the carbon-wrapped rotor spinning quietly inside Tesla's latest drive units represents something more significant than a clever engineering trick. It represents a company that decided the old trade-off between speed and efficiency wasn't a law of physics, after all, just a problem nobody else had solved yet. So, is this the moment the electric vehicle race effectively ends? With one company simply outbuilding everyone else on every front at once? Or is the gap smaller than it looks, with the rest of the industry closer to a real answer than the headlines suggest? That's the question every automaker in this story is now racing to answer, whether they're ready to admit it or not.